The picture that you're looking at now shows the Auroral Observatory. This is where my unit, Tromsø Geophysical Observatory, is located. The picture was taken in 1932, so almost 100 years ago. But the facilities here are still intact, so one can actually go up here and take the same picture even today. So Tromsø Geophysical Observatory, we're a fairly small unit, and we're sort of a special unit in the context of university, since we don't do teaching. Instead of teaching, we have the so-called observatory obligation, which the university received when it was established around 1970. So our job is basically to continue the long time series of geophysical measurements and monitoring of the upper atmosphere, which was inherited from the Auroral Observatory in Tromsø when the university was established. So just a sneak peek upon some of the long time series that we're responsible for before I start talking about Aurora. What I show here is the declination or direction of the magnetic needle or compass needle in Norway as function of time. And the plot starts in 1750 and goes all the way up to present day. And different colors represent different magnetic observatories. So you can see that the magnetic field or direction of the magnetic field has changed dramatically since measurements were started in the 1700s. Today we're operating the red and green and blue and yellow lines, observatories. So the red one is in southern Norway, the green one is here in Tromsø, and the blue one is in the Barents Sea, and the yellow one is at Svalbard. So as you can see, for example, during the time the observatory in Tromsø has existed, the compass needle have moved from pointing -5 degrees, 4 degrees west to its current direction, which is close to 7 degrees east. So this shows basically why it's important to monitor the Earth's magnetic field, and also why the mapping authority needs to update their maps every 5 years. Otherwise, people navigating will get out of course. Okay, enough about that. Let's have a look at the Aurora. I always start talking about the Aurora, showing this picture of a portion of the universe. And normally I ask the audience what we find most of in the universe. And the picture basically shows it. Most of the universe is emptiness or nothing at all. And all the bright spots you see are stars. And next question is then, what is the average temperature of the universe? It's close to or around 4 Kelvin. So it's very close to the absolute 0 point in terms of temperature. And all the bright spots are of course stars. And if we take the sun, what's the temperature of the sun? The surface temperature is between 5,000 and 6,000 degrees. And if you move out into the corona or the solar atmosphere, you get temperatures above 1 million or several millions. So what happens if you have points of very high temperature and they are surrounded by a vast emptiness of an average temperature of only 4 Kelvin? What happens is that the hot gas around the star will try to diffuse out into this emptiness. And this creates a continuous wind flowing or blowing out of every star that we see on the sky, so-called stellar wind. If we zoom in on our sun, we have the situation here. We don't call it a stellar wind, we call it the solar wind. And the solar wind is then this hot plasma or hot gas in the solar atmosphere flowing out in all directions. The picture tries to show how this wind blows out towards the edges of the solar system. You can see the planets there surrounding the sun, and then eventually the solar wind encounters what we refer to as the interstellar medium, and that's sort of the outer boundary of our solar system. So now what happens when this solar wind encounters the planets? And in particular, what happens when it encounters Earth? Earth has its own magnetic field. So what happens is that the solar wind will then collide with Earth's magnetic field. And since the solar wind is plasma, charged gas, the magnetic field will interact with the plasma, and a cavity is formed. This cavity we refer to as the magnetosphere. The solar wind compresses then the magnetosphere on the day side and then stretches it out in a long tail, so-called magnetotail, in the anti-sunward direction. If we go more schematically into this, we see here Earth seen from the side, and the solar wind comes in from the left. Since it's a highly conductive plasma, it also carries with it its own magnetic field, which originates at the sun. And when the solar wind then interacts with Earth's magnetic field on the day side, and the magnetic field lines are oppositely pointed, we get what we call magnetic reconnection here on the day side. Magnetic reconnection is simply merging of magnetic fields. So after the occurrence of magnetic reconnection, Earth's magnetic field lines in the polar regions are connected to the solar wind. So on the North Pole, the field line will actually be traceable all the way to the solar surface. But the solar wind moves. It has an average speed of about 300 kilometers per second. So it will pull Earth's magnetic field lines into the magnetotail, as was seen in the previous picture. And in the magnetotail, the magnetic field lines are again pushed together, and we have magnetic reconnection occurring here as well. That reattaches the magnetic field lines to the poles of Earth. Now, this is a very eruptive or very explosive phenomenon. So, and the magnetic field lines that are stretched will then be thrown towards Earth from the night side, like a slingshot. And this accelerates plasma particles like electrons and protons to precipitate along the magnetic field lines and into the polar regions. And that's basically what forms the aurora when these injected particles collide with the atmosphere here on Earth. So while this precipitation goes on, the magnetic field lines will continue to drift towards the day side again. And this way we form the so-called auroral oval. And this is what we try to illustrate at the lower, at the bottom of this figure, where the magnetic field lines are numbered like on the top figure. And we get this auroral band. If I show you the next figure, on the right there is a picture of the auroral oval. So you can see the sun is illuminating Earth on the day side, and then we have the most of the particles being injected from the magnetotail on the night side, and then still precipitating while magnetic field lines are drifting towards the day side again. Now, the figure to the left, you can see two circles that are rotating. That's the auroral oval, and the secret to understanding the figure is in fact that Earth is rotating and the auroral oval is static compared to where the sun is. So the thinnest part is the day side auroral oval, and the thickest part is the night side. As you can see, the rotation of the Earth brings Scandinavia under the nighttime auroral oval once a day. So you can actually read off the time at the top of the figure when the likelihood of seeing aurora over Tromsø is highest. So it's late afternoon, evening, until early night approximately. You can also see here how the oval sweeps over Svalbard, making that a perfect location to investigate the aurora on the day side. Another important aspect of this figure, if you look at the geographic latitudes here, which are the black dotted lines, you can see that northern Norway is located at the same latitude as the middle of Greenland, northern Alaska, northern Canada, northern Alaska, and northern parts of Siberia. And those are very cold and inaccessible areas, while here in Norway we have the Gulf current flowing up through the North Atlantic and making the climate here much more hospitable than in the other comparable areas. And that makes Norway a very good location for studies of the aurora, and that's also why we can find a huge amount of infrastructure attached to that field of study here. So what causes the colors of the aurora? There are many different colors. Of course, the most dominating color is green. But sometimes you see red on top of the aurora, also red at the bottom of the green, also blue and violet, purple colors. And sometimes it's even gray. When you see gray aurora, it's actually because it's so weak that only the receptors in the eye that see contrast are the only ones detecting it, and then you don't get the color information. But the main colors are purple and green and red. To understand why we have these colors, we need to do some repetition. So here's a picture of the atom. And as you remember from studies, the atom consists of a positive nucleus or a core, and then there are electrons flowing in preferable orbits around it. And there are just as many protons in the core as there are electrons. Now, in the atmosphere, we have mainly oxygen and nitrogen, and chemical variations of those. So what happens when electrons from the solar wind follows Earth's magnetic field and precipitates into the atmosphere? We can get collisions. So an electron precipitating will have a lot of energy, so it will most certainly ionize a lot of gas before it starts creating color. But now we're focusing on the aurora, so here's the mechanism for creating the color. So here we see a simplified picture with a nucleus in the center and an electron orbiting it. This can, for example, be oxygen, but then we're just drawing one electron opposed to 8 as in reality. And here's our charged particle coming from the solar wind. It collides with the electron in orbit and then lifts that electron into an excited state of the atom. Now these electrons, they don't like to stay in excited states, so it jumps back down to its original orbit as soon as possible. And to get rid of the extra energy it has in the excited state, it needs to send out that energy in form of light. And that's basically what happens when we have aurora, that the local gas re-emits the energy it absorbs from the charged particles. So in principle, when you're looking at the aurora, it's just many short flashes of light being produced this way. Next slide shows a movie illustrating the same thing. So here we have the electron orbiting the nucleus, and then we have a charged particles coming in, colliding with the electron, lifting it up to a higher state, and then it falls back down in its original state and sends out a photon. And the energy it emits determines the wavelength. If you were to look at the aurora with a spectrograph or a prism, you would see that there are hundreds of emission lines from the aurora. as you know, that if you look at the sun, you will, or the sky, you will get a spectrum of a rainbow. Well, we have these discrete lines in the aurora being produced in the fashion I showed you just now. So for example, here's a typical spectrum. We have the most common green line. And then we have the red line here and the blue line over there. The blue line is 4278, 4278. I guess it's that one. And then the green line is 557 nanometers, and the red line is 630. Those are the ones that are most common to see. The green and red line are produced by collisions with atomic oxygen that exists in abundance at the top of the atmosphere. And the blue line is caused by N2 plus, so ionized nitrogen. And the nice thing is that if you look at the aurora, you can determine what gases exist in the atmosphere just by looking at the spectrum from them. And this enables us also to study the atmospheres of other planets. For example, Jupiter and Saturn have strong aurora that's possible to observe from using space telescopes, and that information can shed light on what sort of atmospheric compounds on those planets. In the future, we might even do the same thing on exoplanets. So my next slide here is basically the same as I showed earlier. It's meant for people staying in Tromsø, because then I could show you that they should go outside to look for aurora at about 1800 UT and stay up until about 1 o'clock UT, because that's when the aurora is over northern Norway. Any questions so far? Some of you, since you're working with machine learning and maybe neural networks and similar things, I added this slide showing what's, because in space physics, which is my field, there is an increasing interest for machine learning. So I just grabbed some examples of what people are using machine learning for in our field. At the bottom there, you can see work that has been done recently by Japanese colleagues, where they train an algorithm to detect clouds and different types of aurora. This plot shows the day before yesterday, and their AI have detected discrete auroral arcs at specific times during the night. And this has become very popular. There's data going back to the 50s that haven't been analyzed. So using AIs helps to do geophysical research and auroral studies. Here's another example where an AI has been trained to scale radar data. So this is an ionogram showing altitudes and reflections of radio waves. And these horizontal lines are values that we identify to determine the electron density and altitude in the upper atmosphere. And there has been several successful studies where they use AIs to predict this value instead of doing hand scaling. And the second thing I wanted to show you is the use of AIs and machine learning to predict the future for space weather purposes. So here you have a magnetic index showing how the activity has been, and that's been used with an AI to predict the future, to see what sort of space weather we get. That brings me to my little video that I was planning to show you. So if I can find the share screen button again. Share screen. And then the video. So now you should see a white circle. What you're about to see is a video with a all sky camera. So an all sky camera is simply a camera that looks straight up and has a lens that enables it to show the whole horizon or the whole sky. So the center of the picture is zenith or straight up, and then the edges is the horizon. So we're north up, south, down, east to the left, and west to the right. So this would be very similar to be lying on one's back and looking up at the sky. So I'm going to show you now many hours of data. It won't take many hours. The curve at the bottom here shows the registered magnetic field at the same time. So the horizontal line, vertical line shows the is the time when we see the picture. So I'm playing the video. It's white now because the sun hasn't gone down yet, but it starts to go down and more and more of the sky becomes visible. And you see some clouds there, some stars shows up. To the right there, you see the moon. And then there is some auroral activity in the north. Notice how it will intensify when we reach this very disturbed part of the magnetic field over here. Of course, the relationship between aurora and the magnetic field is that there are electric currents in the aurora, which creates magnetic disturbances on the ground. You see some red color there. Then it intensifies. And this is the onset of the geomagnetic storm. And you get basically aurora covering the whole sky and far to the north and far to the south beyond the field of view of the camera. And you can also see that there are different types of aurora according to when during an event like this occurs. So the lucky people being outside this night had plenty of aurora to see. And we're soon approaching, yeah, it's clouding more and more over in this video, so but you still see some aurora in the background there. Any questions? I mean, this basically concludes what I was planning to talk about.